Assalamu alaikum everyone. My name is Siyaan Qureshi. I'm a third year, and today I'll be covering acids, bases, and buffers. Apologies, I'm a little bit sick right now, so please do bear with me. And my phone number is down there, so if you have any questions, feel free to reach out on WhatsApp. And with that, I hope we know it's going well. Let's begin. So, firstly, here are the learning objectives. Um, I put them here for you so that you can try and target your studies. That way, that you can easily figure out how to answer the question in the exam, because we haven't yet had questions from your doctor, so I can't exactly give you advice or practice questions as such. But by making sure we target these objectives, inshallah, you'll have the highest chance of covering all your bases for the exam. Like, let's say, for example, define sources of volatile and fixed acid production and the normal routes of loss. Like, this could be an SEQ if you wanted to, you know what I mean? So hopefully that makes sense. And the objectives for the next lecture should be these three. I put them here because both lectures are very intertwined and connected. And so if it's possible, I do recommend you guys study both lectures together. If it's not, that's perfectly fine. But if you can, try and do that. It will help you out, inshallah. But yeah, so this is what we're aiming for the next lecture. But right now we're covering the groundwork and the basics. So we'll go to objectives 1 to 4, and I'll do my best to try and simplify the chemistry because there is some chemistry. Um, but before we start, why is any of this important? Well, if you remember from foundation, this big thing called homeostasis, right? And part of that was controlling the pH within the body. And that was important for many things like the proteins and enzymes in our body. It also affects the blood, it affects our muscles, even our heart, the way it contracts. It affects the nervous system, it affects our bones. So it affects a lot of things. And I just put a slide in here just so you remember like this concept is extremely important. Make sure you can understand it in the next lecture as well, because it's going to stick with you for the rest of your career, most likely. Like, we're still taking it, we still talk about it. In fact, it's going to come on the steps, it's going to come up in your clinical practice. And so just make sure that this concept is very clear, because I know a lot of people who still struggle with this, like even later on as a senior. Um, so, anyhow, we're going to start with a chemistry review. And I know you guys took medicine. Chemistry might be the last thing you want to see right now. I'm sorry about that, but it's necessary. But hopefully you guys can remember most of this from school, and I'll make it easier. So let's just like make this as brief as possible. And I did put a little chill guy over here for us so that he can watch over us, give us some good vibes and chill vibes, get us through this very quickly. And so let's start with some silly definitions of an acid. Well, an acid is something which is going to give us hydrogen ions. We can also call those protons. Whereas a base is something which is going to take protons or hydrogen ions off us, okay? And so a weak acid is actually going to give us protons and an anion or a conjugate base. And this happens in equilibrium. What do I mean by that? I mean that we have a forward reaction over here. We see that forward arrow and a backward arrow. So it's going both ways. Like, this weak acid is turning into protons in the conjugate base. And also the conjugate base is adding with protons to make weak acid. So both reactions are occurring at the same time. All right. So it's balanced. It's not just one way or the other. It's both ways. Okay. Now, a major example of this in the body is carbonic acid. It's a weak acid, and it's going to dissociate or give us protons. All right. And a bicarbonate ion, which is its conjugate base. And again, like I told you, likewise, these two can basically add up and give us carbonic acid. All right. Now, our next slide, we're talking about controlling pH, etc. But what is pH to begin with? Again, a quick refresher from school chemistry. pH is a scale of proton or hydrogen ion concentration. And what we're going to say is that this scale is actually a bit special. Why? It's a little bit quirky. It's a little bit weird, all right? How so? Well, most scales we know, when you go up the scale, you go up as well. Like, whatever you're measuring is increasing as you go up the scale. What pH does is it's a little bit, quirky, like I said. It's going to do the opposite. When we go up in pH, we're going to be going down in concentration of protons. All right. And we can see this in this image over here. We have neutral pH of 7. All right. So as we go up towards, let's say, drain cleaner at 14, the pH is increasing, right? But the hydrogen ion concentration, the proton concentration, is decreasing. Okay. Um, on the other hand, when we have 7 again, and we're going down the pH, so we're decreasing in pH to, let's say, battery acid at 0, then we are increasing in proton concentration. So the more you go towards 0, the more protons you have, concentration-wise, and the more acidic. And like we already mentioned, the higher you go in pH, the more basic, the less concentration of protons. All right. Now, I don't, this doesn't really work for me, but if it works for you, like please use this. I know it looks a little bit silly, but honestly, medicine, like one big tip, honestly, is just figuring out how you learn, like what is your learning style. And for me, this doesn't work, but sometimes some silly acronyms can stick. And yeah, so if this works for you, by all means, please use it. And any other silly acronyms, etc., like, use those things. They might seem dumb, but they carry so hard in the exam, I'm telling you. Anyways, back to the point. So the phrase is acid is low, like the L in lemon. Base is high, like the H in heaven. So yeah, if that helps you, then perfect. And I'm sorry, there's an elephant in the room, guys. I know it's on my slide. The formula. Everyone hates formulas. We're med students, but honestly, this one isn't too bad. It isn't too bad, guys. Let me break it down for you. So, firstly, it's just telling us pH equals. So, pH is, all right, minus log 10. We'll get back to that. And then hydrogen ion concentration. So, we know what hydrogen ion concentration is, all right? Minus log 10. Let's break it down to minus. Well, minus, what is that doing? It's telling us that this scale is special. Why? Because minus is flipping it for us. It's saying that when we go up from 7 to 8, that difference is not an increase. This minus is saying that actually, when we go from 7 to 8 in pH, the concentration is decreasing. So this minus is symbolizing that part, which I was mentioning before, okay? Log 10. Well, usually we think in steps of 1. We go like 1, 2, 3, 4, and we count that way. But what log 10 is saying is actually, you know what, guys? Let's go 0, 10, 100, 1,000, 10,000, 100,000, a million. So log 10 is basically counting in steps of 10. All right? That's why I put this times 10 over here. So let's apply this now. We have minus log 10. So we're at 7, and we want to go to 8. So it's a step of 1, all right? But it's minus. So we're saying that actually the concentration here from 7 to 8 is decreasing, all right? Log 10 means that this step is actually a step of times 10, all right? So what does that mean now? It means that we have a decrease of 10. So it's a decrease, 10 times decrease of hydrogen concentration, all right? Now let's apply this one step further. Let's say we're going to go to baking soda at 9 from 7. That's going to be 1 step, 2 steps. So it's actually going to be 10, 100. It's going to be 100-fold decrease. And hopefully this makes sense now. Just for clarity's sake, if we're going from 7 till 4, then that's going to be 3 steps, right? 1, 2, 3. That's going to be 1,000-fold increase because we're going down the scale. It's negative, right? So we're going to be going down the scale, up in concentration. All right. So 7 till 4 was a 1,000-fold increase in uh, proton concentration. So sorry that was a little bit lengthy, but hopefully that will make sense, and that makes now your foundation is set, and hopefully you don't get questioned on this in your exam. But I recall we did. I think it was actually in mole. So if you guys have that in mole too, then there you go. But otherwise, yeah, hopefully that will make sense now, and we can now apply this to the blood, where we have this amazing formula which we understand now, okay? And let's say we're told that the normal concentration of hydrogen ion in the arterial blood is this number. I won't even bother to read it out, okay? But this is a concentration unit, and this is the number, okay? And all we're gonna do is we're gonna plug this number into the concentration, and If we put this in our calculator, minus log 10 times 4 times 10 to the power of negative 8, we're going to get an answer of 7.4. And that is our magic number. That is our physiological pH of the blood. All right, so we should know this. We should know this. But it's medicine, guys. It's never that easy, is it? So we actually have to memorize a range, all right? Because nothing's going to be perfect. It's the body. Things are going to go up and down a little bit. So we have a range to memorize, and that range is 7.35 to 7.45. That is our normal physiological pH range, okay? And we can see this on the graph as well. So from 7.35 to 7.45, everything in between that's lying in between is our normal range. Now, if we look to the sides, we have, let's say from the right first, 7.45 and above. Um, we said we're increasing pH, we're decreasing proton concentration. So we're going to call that alkalosis. That's going to be less acidic. It's going to be more basic, more alkaline. So that's what we call alkalosis, 7.45 and above. And on the other hand, below 7.35, we're going down towards like let's say 7 or 6.8, then that is going to now be more acidic. It's a lower pH, there's more protons, there's more hydrogen concentration, and what we're left with is acidosis. All right, so it's in the name acidosis, you're more acidic, alkalosis, you're more basic. Perfect. And our normal range, we have to memorize 7.35 to 7.45. So above this is alkalosis, below this is acidosis. Cool? Our last definition for the chemistry review is going to be a buffer. And the chemical definition is an acid and its conjugate base, or a base and its conjugate acid. But before we continue, let's just think about it generally. What does buffering mean? You might have heard of buffering zones. You might have heard of like, just in general, buffer means to basically give a margin, to like basically to cushion, to decrease the effect of something, okay? To absorb the impact. And one way you could think about it is like a monster truck. You might have seen they have these massive tires and massive suspension, crazy shocks, crazy coils, etc. Okay? What's the point of all this? Well, basically, a monster truck can just devastate right through whatever you throw at it. Okay? It's gonna eat up all the bumps, it's gonna absorb all the shock, the impact, etc. when it's driving through dunes or rocks, etc. All right, you can imagine that vividly, right? That's exactly what a buffer is doing. A buffer is going to absorb the shock of a system. What shock are we talking about specifically? We mean the pH shock, the pH change. If you suddenly add a bunch of acid or a bunch of base to a solution, we don't want that pH to change. We want a smooth ride. We want to keep it stable and balanced. And that's what a buffer does. A buffer is going to buffer out, it's going to stabilize and balance and absorb the shock to the system. All right. And so back to the definition of an acid and its conjugate base. Wait, we've covered this. An acid and its conjugate base. There we go. That's our first example of a buffer. All right. Carbonic bicarbonate ion buffer system. And we'll talk about that later in the lecture. Let's just move on now to our last slide. This concept. Again, no need to memorize this. This is chemistry. I'm just introducing you guys to this if you haven't done it so already, just to make sure like you can understand this basic concept. And this is pretty much how a buffer is working, all right? So if you guys have ever seen Russian dolls, you would know what they're famous for. You can basically, well, other than stacking them inside each other, you can tip them to one side, and what they do is they'll bounce themselves back up. So you tip them, and due to their low center of gravity, they bounce back up. And that's exactly what I'm trying to get at here with equilibrium and this principle. What it's trying to say is that a buffer is an equilibrium, right? It's going to work in this way. This principle is in all equilibriums, all right? And a buffer is an equilibrium. So how it works is, let's say you have a bunch of stuff on one side, a bunch of stuff on the other side. If we add an excess to one side, what do we have? Obviously, an imbalance. It's gonna be unbalanced, right? Now, what this principle says is that an equilibrium, it wants to be balanced, like a Russian doll. It wants to stand back up again. And so it's going to actually shift its weight a little bit and counteract the effect. And that's exactly what we see. So we had an imbalance and we pushed them to the side, and now we have a balance again. And now let's take this one step further and use as an example for chemical buffers, okay? So let's say now we have um, we have a lot of acid on one side and a lot of base, but they're the same amount, so it's stable. Now we added more base to one side, okay? So now we have acid and we have a lot of base. What can acid do? We said acid can give protons, remember? So oh, sorry. You know what? I should say the other way around. My bad. So this is the acid and this is the base, all right? And so we added a bunch of acid to one side, and we said that now it's unbalanced, okay? So what can the acid do? The acid can give itself, some of itself, into making a base. So that's what we see here. So we lost one of the acids because it went to this side. It turned itself into a base. It gave hydrogen ion and its conjugate base. So it became a base, right? And likewise, when we flip it around, the same thing happens. If we have um, base on this side, we add more base, okay, and we have acid and we have more base on this side now. Then what happens is the base can turn into acid, all right? Here you go. The base can turn more into acid. Um, so yeah, that's pretty much it. And how it does that, that's chemistry. We don't really care. Let's move back to medicine now. Thank you for sticking with me. Okay, so our first objective is defining sources of volatile and fixed acid production, as well as the normal routes of loss from the body. Now, that's a little bit wordy. Let's first figure out what is a volatile and what's a fixed acid. Well, volatile means that basically something can be easily evaporated or vaporized. Like, for example, perfume. You spray it on your hand and it will vaporize into gas and you can smell it and it's nice and blah, blah. And so that's what volatile means. So a volatile acid is something which can vaporize easily. And so it makes sense that these are the type of acids which are going to be released in the form of gas from our lungs. All right. Now, on the other hand, fixed or non-volatile, it's fixed. It can't change into gas. It's stuck as a liquid. So how do we remove this instead? Well, what's our major excretion of liquid? Urine, right? So it's going to be excreted by the kidneys as urine, inside the urine, sorry. Um, Now, just to give you the examples of what these are, the volatile acid, our main example, our only really, important example is CO2, carbonic acid. All right, and we'll talk about this more in the next slide. Let's just get rid of the fixed non-volatile acids because they're not as important, but they were mentioned in your doctor's slides. So, what are the sources? We already covered the loss. We said the loss is through the kidneys as urine. So, what are the sources of these? Well, diet. Let's say you drink a bunch of Coke, okay, or Pepsi or Kinza, sorry. Um, you took some type of drugs, like let's say aspirin, because aspirin is also called salicylic acid, all right? Um, Keto acid and lactic acid for metabolism. I won't talk about this because I think it's done in mole. Catabolism or the breakdown of amino acids. Again, this is to do with mole, but I think it's mole too. So I'll quickly explain. Basically, amino acids, many of them can form disulfide bonds, especially cysteine. And so this is just to connect the dots. You guys don't need to memorize this. It's just to connect the dots. That yeah, amino acids have these sulfide bonds, and that's where the sulfur is coming from to make sulfuric acid. On the other hand, phospholipids. I think you guys have covered this, the phospholipid bilayer. And so obviously it has phosphorus, and so that's a source for phosphoric acid. Sorry. All right. Now, the source of carbonic acid, hopefully you guys can remember this from school, from foundation, etc. It's respiration, guys. It's the classic glucose and oxygen and all that type of stuff, right? It's happening in our cells, etc. And so yeah, that's going to be our source of CO2, our main source. And it's a waste product. We gotta get rid of it. But it's acidic. So what do we do? Well, we have our amazing red blood cells, and they will actually, the CO2 is going to diffuse into the red blood cell. And our red blood cells have this enzyme, carbonic anhydrase, carbonic acid, anhydrase, to do with removing water. So what we do is we get CO2 and we turn it into carbonic acid. All right. And now this can be transported around in the ECF very easily, or within also the RBC as well. But what's special about this is it's an equilibrium. We already mentioned this, right? The carbonic bicarbonate buffer, right? and we'll explain this more later. But this is the buffer which is going to be really important within our ECF. All right. And so this is the source, the cells, respiration, and this is the loss, the lungs, because what happens is that it gets transported, right, in the ECF. And then when it gets to the lungs, carbonic anhydrase is there again to save the day. And it converts carbonic acid back into CO2, and then that can be exhaled from our lungs. All right. So that's objective one done. Now let's talk about objective two. So we got to identify the major intercellular and extracellular buffers in the body. And so the first one, the most important one, you can't forget this, is the carbonic bicarbonate buffer. All right. And what's important about this is that it actually has two compensatory mechanisms. All right. It can regulate the buffer by the lungs as well as the kidney. And I'll explain that later um, on our next objective, but let's just understand for now, this is the most important ECF buffer, all right? The other buffers aren't as important, but they were glossed over in the lecture from the doctor, so I'll try and just quickly get over them. The first one I want to talk about is an important intracellular buffer, which is the phosphate, the inorganic phosphate buffer. And why is it important intracellularly? Well, it's got a high concentration there. It's got a low concentration in the ECF, which is why it's not a good buffer in the ECF because there just isn't enough of it. All right. Um, on the other hand, hemoglobin is going to be important for actually neutralizing and sorting out, controlling volatile acids. All right. So like so like basically like carbon dioxide building up in the RBC, which is RBC. It's a cell, right? So this is an intracellular buffer, and yeah, this is the most important for volatile acids, like we just mentioned, the carbon dioxide and the carbonic acid. All right, so within the RBC, intracellular. So don't mix these up, by the way, please, because they try and trick you in questions with this, the whole ECF and ICF thing, uh, intracellular buffer and extracellular buffer. Sorry. So, anyways, um, our last buffer we're going to talk about is the plasma proteins. And the main example of this, it wasn't mentioned in your slides, but you should know, is albumin. That's the main plasma protein that's going to do a lot of buffering as well. All right. The way this works, again, I don't know if this is done in mole yet or if it's mole two. I think it was mole two, is that amino acids have basic and acidic groups. All right. And so these groups can contribute to the pH and act as buffers. And plasma, it's in the plasma. So plasma proteins are happening extracellularly. Okay, it's extracellular buffer because it's happening in the plasma, the blood. All right. Um, how one important amino acid that you might see in questions from external resources is histidine. Again, this is a mole thing, so I'll leave it for now. But it's good to know if you have extra time, look into histidine and how that affects the hemoglobin and plasma protein. But at this level, the doctor hasn't mentioned it, so if you want to skip that, please do. Our third and second last objective is to describe the respiratory and renal mechanisms of pH control. Before I do that, let's just quickly talk about how the buffer is actually working. Just let's follow this really quickly. So we have CO2, it entered, and it, in the RBC, helpfully from carbonic anhydrase, it became carbonic acid, and it can also become bicarbonate ions, right? And so what we have here is a balance between three like components now, okay? And so what happens is that if you have if you have a lot of hydrogen or proton ions, okay, protons or hydrogen ions, then you're going to shift the balance more towards this side because, like, just imagine this is stacking up and stacking up and stacking up. All right, sorry. It's going to shift more towards here, and so this is compensating for this side. At the same time, if you have too much CO2, it can shift more towards this side, and vice versa. Let's say you don't have enough. You have the um, the pH is too high, right? That means that the concentration of protons is too low. So you actually have an excess of these two and a lack of this. Then yeah, you can actually this can go more towards here and this can go more towards here and it'll balance out. So these three things are like um they're balancing each other out. Okay, they're like three glasses, okay? And you can pour liquid from each glass from one side to the other, but you have to go from left to right or from right to left, all right? And so if you have a lot on one side, it will try and shift naturally and balance it out in the same way. And if you have too little on one side, then the one which has more will also balance out. Um, I think I made that too complicated. I think that makes sense, right? I'll move on. I think that's honestly more than enough for you to understand from now. And yeah, now let's talk firstly about the lungs mechanism of pH control. So what are the lungs going to do? Well, we understand this whole shift from left to right to left now, okay? So what the lungs can do essentially is is it can remove CO2 faster. So like I said that we might want to shift it more towards this side. And how do we do that? We have to like make this glass more empty so that water can flow this way, so that these concentrations can trickle down that way. And so how do we do that? Well, we can breathe out more CO2. If we breathe more CO2 out, um, we have less CO2 now. So carbonic acid is more likely wanting to become CO2. All right. And so that's the control from the lungs. So it's going to basically, this is hyperventilation. When you breathe a lot, you're removing CO2. Now, one thing which some people might confuse is like, oh, well, if I'm breathing a lot, why is CO2 only decreasing? What about O2? What about, no, you got to understand that O2 is already saturated, but CO2 isn't yet. Like when we have O2 in our body, like inspiration, we already have almost 99, percent saturation. So when we breathe more, it's the amount of O2 we gain is negligible. However, um, CO2 is the limiting factor in our breathing, right? When we breathe a lot more, we're able to actually take more CO2 up. Okay. And so that's why also, if you don't breathe enough, let's say you're breathing slower and slower and slower, we can't remove the CO2 fast enough. And that's what happened to suffocation. Suffocation, oh no, the guy can't breathe. No, what happened is that basically they had a buildup of too much CO2 in their body, and then they end up passing out usually. So that's pretty much the mechanism of lung control, where you have, I put soda here, like Pepsi or Kinza or whatever, to show you it's acidic. And so to remove the acid over here, you're breathing out. But like I said, if you can't breathe out fast enough, for example, like let's say you took some drug and you have a respiratory, drive center depression, all right, like you're breathing very slowly because of the drug, then you might end up having too much CO2. It becomes too much acidic. You're going to have acidosis and you'll pass out and possibly die. On the other hand, if you breathe a lot, you're hyperventilating. Let's say you're panicking, you're anxious, so you're breathing like really fast, then you're going to exhale too much CO2, and that's going to shift the balance more towards here, and it's going to leave you with less because you're shifting the balance this way. It's going to leave you with less hydrogen ions or hydrogen concentration. And so we said this is a lack of this, like lowering hydrogen is increasing pH. What does that mean? It means alkalosis. So we're actually going to be left with alkalosis by doing this. All right. And here's a little like flow chart. So let's say we have low pH, it's acidic. We exhale a lot of CO2. Okay. CO2 is going to help us to shift the balance more towards this way, right? By removing CO2, we're allowing it to flow more this way. And so what you're left with is with less CO2, you're going to have a normal pH again. So your decreased pH will increase a little bit now. All right. On the other hand, oh, sorry, this is the same thing I'm talking about here. So hyperventilation is basically going to be causing alkalosis. As we mentioned here, we're breathing a lot of CO2 out. And so this is going to shift more towards here to fill in the gaps because we removed a lot of CO2. Then this is going to shift over here. And because this is shifting here, we're being left with less protons. Less protons means more pH. More pH is called alkalosis. So this is called primary respiratory alkalosis. On the other hand, hypoventilation is going to be the opposite. So we're getting too much of this now. It's backlogging, it's building up, it's building up, it's building up. Oh no, we have too much protons. Too much protons, that's low pH. That's acidosis. So that's primary respiratory acidosis. Primary meaning that the cause is actually from the lung mechanism, all right? And secondary and the compensatory is going to be uh, the next lecture, all right? So right now, I just want to make you guys understand what this control system is and how, physiologically it could be messed up if, you're anxious or, you're sleepy or not sleepy, like you took a drug or something, all right? Um, Now, the second part is the kidney. The kidney is going to control this buffer by excreting urine. All right, we know that. How is it going to exactly control it? Well, two steps. Number one is it can increase the amount of bicarbonate ions that are reabsorbed. All right, so we lose bicarbonate into the urine, but we can reabsorb more of this. All right, that's the first thing it can do. And secondly, it can actually kick out or secrete the hydrogen ions. And so, well, firstly, secreting hydrogen ions is going to help us to um, increase the pH, to lower the acidity, right? It's going to help us to, if it's very acidic already, okay, mainly this is going to help us with um, decreasing acidity. So we have a low pH right now, and we want to get it back to normal. So we're going to basically reabsorb more bicarbonate ions. And bicarbonate, as we know here, is going to be able to accept the hydrogen ions. All right. So it's going to be able to help like neutralize the acidity. At the same time, we're gonna kick out more of the protons. We're gonna kick them out, okay, back into the urine. So that's gonna number one, decrease the acidity. But number two, it's actually by kicking these out, it can actually bind with bicarbonate in the urine, okay, because not all the bicarbonate can be reuptaken. Like we have these transporters, etc., which you guys should have taken the other lecture already, but they reach a certain like threshold where they can't work more, right? Like you get to a max. But what we can do now is rather than try and absorb more bicarb, it's already full. All the gates and channels and blah blah are full. What we can do is actually um, by secreting hydrogen out, it can bind to the bicarb and make carbonic acid. Okay, and the carbonic acid, there's carbonic anhydrase again. Our friend comes back again. It will help turn carbonic acid into CO2 and water, and CO2 can passively diffuse into the cells. And then again, carbonic anhydrase can turn it back into carbonic acid and then bicarb. So that's like an indirect way of basically making new bicarbonate through bicarbonate outside, turning it into carbonic acid, turning it into CO2, and then taking it back in because we already have, like, we can't take more bicarbonate. All our channels are full, but we have this passive diffusion from CO2 that can help us out. All right. And so that's how we basically um, made a low pH back to normal by reabsorbing more bicarbonate and by kicking out the hydrogen and through a indirect way, increasing CO2, increasing bicarbonate. All right. Um, the last objective, and this is the last slide, by the way, is simply defining the normal values of arterial gas analysis. There's honestly not much I can explain about this. You'll cover more of this in the next lecture. I just want to leave you on this slide so you can like take this, look at it, and when you go into the next lecture, it's best you do memorize these ranges because there's no easy way to say this. You gotta memorize these ranges. All right. We've already talked about the 7.35 to 7.45, so that should make sense to you. But the CO2 and the HCO3, this is gonna help you figure out if something is respiratory or metabolic. That's gonna make sense in the next lecture. But I just want to leave you on this so you can memorize these ranges, and when you start the next lecture, it'll be very easy for you from then on. All right. For any feedback, please do scan this QR code. I appreciate it. And thank you so much. Once again, apologies. I'm a little bit sick right now, so it wasn't my best, but I did what I could. Please feel free to text me for any questions. I would be more than happy to help. And thank you guys. Best of luck. And yeah.